Today we will continue to discuss about the stresses. Well, stress is in internal stress, internal load actually. So if a body is subject to external load, inside the body there will be some actions and reactions, and those internal forces are called stresses. And here are the here is the definition of the stress. Okay, this is a three-dimensional body, and stress is defined at a point, for instance, O. And when this body is subject to external load, these internal stresses will be developed at a point O, and we can define three perpendicular planes, and each plane will have a three component of distributed load or forces. So 3 times 3 give us 9 components. This 9 by 9, 3 by 3 component stress is the internal forces defined at a point O. Okay, remember that stress is defined at a point O. Okay. So in mathematically, we can have many different expression for physical quantities at point O. There is quantity called scalar and vector and tensor. Why do we need to have a 9 component to describe some physical quantity like stress at a point O? Get 9 components. Well, let me let's say we have a same body like that, and I'm trying to explain different physical quantity with a different notation. One is the scalar, like temperature, density, and these terms are called scalar, and we only need one value. For instance, let's say we apply some heat or external temperature, then this body will be heated, and at a point O we will have some temperature. Okay, then what is the temperature at this point? The answer will be just T, just one single value. That's the temperature, and that is called just scalar. Same for density. What is the density at this point O? Just we can say rho, a value. But now we are let's say this whole body is moving in a certain velocity. So let's say whole body is moving certain velocity, and same for this point O. Point O will have velocity v together with the whole body. And if I ask what is the velocity at this point O, the answer will be v. And this physical quantity we call what? Vector. Velocity or acceleration, and this kind of physical quantities are called vector. Vector, in different sense, it should have not only magnitude, but also it should have some direction, right? That is what the vector is for. So vector has 3 components. For instance, v, we should have a vx, Vy, and Vz. 3 components. Again, scalar, we just need a 1 value. And here, vector, we need a 3 component. Again, pay attention to where we define this physical quantity. We define this physical quantity at a point O. Okay, point O. And same for here. Now, let's say this body is subject to external load. And as we learn, there are many different types of internal forces that were developed inside the body, depending on positions. And now we pick the 1 point O, and let me ask, what is the stress at that point O? Okay, what's the stress? Well, stress is like you. If you feel under pressure, you feel a lot of stress inside your brain or body. It's the same for body. This body is subject to external load. Then this one will be subject to they were developed internal forces, and those internal forces will vary from point to a point. So again, if I ask what's the stress at a point O, the answer will be 9 components. Okay, so 9 components we just learned. What does each component mean? Well, again, at this point O, we can define 3 perpendicular planes which will pass through this point, and each plane we will have 3 components of a force. And that's why we have a 3 by 3, 9 components. So do not just say each component has some independent meaning. I would say the whole 9 components has represent a stress. I mean, same concept as the ballast and same concept for a scalar. Stress itself, this one is the representing the internal forces at a point O. Okay, this is a very important concept, and this concept will apply to a strain too. Okay, strain. So stress and strain, we will study more about the strain later, but the concept will be very much similar to this stress. The major concept is this is not just a single value. There will be 3 by 3 components defined at a point O. See, in spring, we have a simple relations, F equal Kx. Well, each term has just a scalar. F is a scalar value, and X deformation is the scalar, and K is just material properties. But that's only for a spring, one-dimensional a body. But now, this concept needs to be extended to a 3-dimensional space, such that stress and strain. See, stress is the same concept as a force, and strain is the same concept as the displacement, deformation. And here I will just say C. And this one is not just single value, as we noticed here. We have 3 by 3, a physical quantity, and same for strain. And similar to these relations, we do have these relations. Sigma equal C times epsilon, and this C is called stiffness, same concept as the K. And in the very beginning of our course in solid mechanics, we said there are three concepts. One is the force and deformation conditions and material properties. Force needs to be equilibrium. That is relate to this F. F again should be in equilibrium, and deformation condition and material properties. That is only for one-dimensional descriptions. And now for the three-dimensional body, we have same stress, is a force, and some deformation condition will apply to a strain, and material properties is a C. In other words, this stress sigma should satisfy force equilibrium, and strain should meet some deformation conditions, and those relation is called material properties. Okay, so those three major concepts will still apply to a three-dimensional body. The only difference is that we extend dimensions, one dimension to a three-dimensional body, but still the concept is the same. Okay, this kind of understanding of concept is very much critical in understanding solid mechanics. And again, whatever we study in this solid mechanics, you need to have a big picture. Okay, now we are in here, stress, and later on we will certainly go to a strain and material properties, and then we will apply these relations to a one-dimensional body. First one is bar and beam and shaft. And that's the whole story. The subject will be covered in this solid mechanics.
Sir,
Yes?
한국말로 질문해보면 저희 스트레스가 9개 컴포넌트가 갖고 있는데 저 입실론 스트레인은 저번에 알려주실 때 F를 그러니까 배를 L로 나눈 게 스트레인이라고 하셨잖아요. 그러면 그것도 9개 컴포넌트를 만족해야 식이 타는 거 아닌가요? 그러니까 제 말은
Well, the question is that now stress is the 3x3, 9 component, and strain actually should be 9 component as well. But we just, okay, this one is a 3x3, and this strain is also 3x3, and this first component we call epsilon xx, and this is defined was L delta x L divided by Ly. Deformation in extractions. So if we have a body like that, and if we extend, this will extend this way, and this one is the delta x divided by this is L, and this is Lx. This is a epsilon xx, and that is just one component out of this 3x3 9 components. We will have different types of definition. Let's say second term and third and so on, depending on the deformation types. This body will deform not only in this way, but also this way, that way, and distortion, and that distortion. All kinds of deformations will be defined at this single point. And depending on those kind of deformations, see in spring, there's only one deformation, which is extension, nothing else, right? But in three-dimensional space, we have 9 different types of deformation. Extension in three-dimensional, and torsion, distortion, and so on. So we certainly have a 3x3 and 3x3, and now That's the answer, okay? And now, how about the C matrix? This is a 3 by 3, 3 by 3. What this will be? This will be 3 by 3 by 3 by 3. See, this is a 9 component, and that is a 9 component. Kind of a relating each component, we need 9 by 9 component. In other words, that 9 comes from 3 by 3, so 3 by 3 by 3 by 3. So totally 81 components. That's another material property defined at a point O. How many components? 81. This is only 9 components, right? And material property, I will ask material property. What's the material property at a point O? How many components? We have 81 material components. So extension 1 value, 3 value, 9 value, and 81 value, and so on. So in tensor, we call this is, I'm not sure you heard about the tensor. In mathematics, we have a terminology called tensor, and this is a scalar called zero order. Zero order tensor. And this is the first order. This is a second order, and third order, first order, and so on. Well, the understanding of tensor is not quite as straightforward for you now. So anyhow, I hope that you can extend the concept to more dimensions. And we will certainly cover more about the strains later. Okay, now, see, we do not have any complicated equations. I'm just describing the concept basically, and here you really need to pay attention to this kind of concept. And now this back to a stress, and again there are 9 components, or in 2-dimensional way is the same concept as a 3-dimensional, but only difference is rather than 3 by 3 we have just 2 by 2 components. Okay, either 3 by 3 or 2 by 2, we have one very much important characteristics of this stress matrix, which is asymmetric. Asymmetry of the stress means that, okay, for instance, in 2-dimensional case, we have this 2 by 2 component, and this body, again, well, we have, as I said, the stress is defined at a point O, and if we consider a small volume, okay, if we consider small volume, and if we cut this part into showing here, and if we have this surface, we will have sigma xx, xy, and upper skin, we will have these 2 components and so on. And that's the surface load which will appear on each surface. Again, this is the sigma xx, this is the sigma xx. See, if we, let me put it in this way, if we consider this body subject to this way, and if we cut here, and if we consider a small volume and pay attention to this one, and we will certainly have this sigma xx and sigma xx. That's what I meant. And same for others. So anyhow, this needs to be a sigma xx, xy, and yx, and yy. So anyhow, sigma xx, xx, and yy, this needs to be a yy. Now, these two diagonal terms are called normal stress and relatively easy to understand since this one and that. And now shear stress of diagonal term is that what is this surface? X and Y. This is the X surface, right? X directional surface. And that's why we call this is the sigma xx, and this one is called sigma yx, right? This is called sigma yx. Do you remember this second index, x, what does it mean? This means this surface is the x. Surface is always represented by the normal vector. And this is x is the normal vector to this surface. And this first index is x means the direction of the x, and y means the direction of this load. So this is certainly called sigma yx. And in negative surface, if we have this one, we also have this sigma yx. And in y directional surface, we same story, same sigma yx and sigma yx. So the point here is that let us consider this shear stress. This is a sigma what? Sigma yx and sigma yx, and upper sigma xy. This is a sigma xy. Okay. This body subject to these all kinds of load, and to be in force equilibrium, this is xx, and y, they are automatically satisfy force equilibrium. But how about this shear load? This subject to these four types of shear stress, and this first consider this sigma yx and this sigma yx. Well, this is the force this way, this is force this way, so there will be no net force. So force is a zero. But these two forces will be act as a couple, and which would rotate this whole body, right? It causes a moment, right? These two forces will cause a moment like that. That's the one thing. And upper and lower y-directional surface, we have sigma xy, and this is this way, that way. And this one is called, this also causes a moment, which is in this way, right? Okay, now, question is that if we need some kind of a condition such that this body should meet a moment equilibrium. There must be some kind of condition for those two stresses component. This is what I'm trying to explain. Sigma xy, this is the small length dx and dy. And dy and dx, and this one is causing a moment, and moment calculate sigma xy okay, sigma xy is the stress, and we need to get the force. What do we need to do? We need to multiply this length So sigma xy xy times dx
dy.
dx, this distance, will give us the force. And same for here, right? Stress sigma xy times dx is a force this way and force this way. And distance dy, we need to multiply dy to have moment, right? And same for here, sigma yx times this distance. What is that? dy. Yes, dy. Then this will be a force in y direction, and same for here, y directional force. And to calculate the moment, what do we need to do? We have to multiply dx. Again, to have this body in moment equilibrium, we need to have this one has to be same, right? Positive and negative. And as you can see here, dx times dy, dy times dx, and conclusion is that, what is that? Sigma xy has to be same as sigma yx. Ooh, it simplify a lot. This kind of symmetry, in other words, moment equilibrium, it comes from moment equilibrium. So actually, this Tn and Nt should be same. Sigma xy should be sigma yx, and it applied to any notations, and these, in other words, Tn should be a Nt. And if we consider different, let's say we have this body, and actually this one will apply to here, and at the other end we will have this one like that, and we will have this way, and at the bottom we will have this way, and this surface we will have this way, and the other surface we will have a this. So anyhow, the one we just noticed here is that only this component and that component, right? Those two components should be the same because of what? Because of moment equilibrium in each directions this way, right? That this guy causing this moment, this guy causing together with, I'm sorry, this one needs to be this way. This, and that. So totally, I mean this one, we get moment equilibrium, and this needs to be, they need to be same. And that is this way moment equilibrium. Now, how about this one? This one and that, we have another one, and so this one and that one, which will cause this directional moment. It's not quite clear, but trying to say is that we have this much, this directional shear forces, and that would also cause another moment equilibrium, and that means this one needs to be this same, and this one same. We have three different moments, this one, and that one. Each moment equilibrium give us condition that this needs to be same as this one is same as this one has to be same as that. So we had 9 components, but now we only need to consider 6 components because those 3 are same as the other 3. So number of independent stress components, how many? We have 6. Again, this symmetry condition for matrix is very important. You know, notation, subscript notation, we can say that sigma ij equal sigma ji. Sigma ij equal to sigma ji. Means that if I and j, let's say x and y, which means yx, xz equal zx, yz equal zy. If say xx, then xx. No further information for diagonal term, but shears give us 3 equations, reducing the number of equations by 3. Anyhow, that's what we call symmetric conditions. Okay, now let's go to strengths. Well, strengths are just a little more complicated than definition of stresses. Again, the strengths are supposed to describe all different types of deformations, and basically the conclusion will be very much similar to stresses. 3 by 3 component, and strain is also second order tensor. Now, definition of strains in 3-dimensional case, and before and after. Let's consider before and after. Okay, we need to go through a little bit of equation, but more importantly, what you need to understand is that these diagram, these drawings, this schematic diagram drawing help you understand why we need to define many different components. See, spring, we only need to define a one component deformations. Now in 3-dimensional case, it needs to be extended. Let's say we have this scale, okay, before deformations. We have a body, this body, we have a scale OCDE scale before deformation, and it subject to a certain load, whatever load, we do not know, we do not have to define yet, but after deformation, it moves, they move to a certain point, O prime, C prime, and so on. How can we describe the deformation correctly, precisely? Ask yourself. Okay, we have a scale like that, and it will deform like this very much. It not only see these four corner, okay, 4 corner, it moves arbitrarily this way. How are you gonna describe the deformation correctly? Ask yourself. Try to answer that. It's not that easy. If this one is just extend this C and D just extend this way, then the answer will be very much simple, right? Where it just extend a certain amount, and only strain delta divided by L will be enough to describe these deformations, right? Well, I need to, let's say, in other words, we have a before deformation and after deformation. Only like that. Okay, this is the deformation and that is the after deformation. And again, the deformation, we can say, okay, deformation, well, it needs to be a non-dimensional, and we just say this one. This one component will be enough, right? Only extractions. Now, well, this body, it deformed not only this way, but also it deformed this way. Well, we need one more. Well, in x direction, we deform this much. In y direction, we deform delta y divided by ly. We have two components. Those two components will be needed to describe this deformation. Do you agree? Yes. So what that and that. Now the question is like that. This is not the scale anymore, and it has a certain arbitrary point movement, and how we're going to describe the deformations. That is the. That's why we need to define this strain. And so we already defined these two components of strains, and other one is actually second one. Okay, forget about these deformations. One deformation will be like that, which means that in extraction, the length, this length is extended, the length is longer. No, it's the same, right? This length is the same, this length is the same, all the same as before, right? So we cannot use this delta x divided by Lx. The length is remain same. So we need to define different way of describing this deformation. What is that? What is the major difference between this one and that? This one, okay, here, the angles don't change, right? The 90 degree, 90 degree, 90 degree, they do not change. Only length change. Here, length do not changes, but angle changes. Okay, so we have to, let's make use of that angle changes. And that's why we, angle is like that. And this angle will be defined by, this is what? This is it X direction or Y direction deformations? X direction. And this one is X directional length or Y directional length? Y, so Ly. So in conceptually, delta X divided by Ly. Remember, this is XX, this is the YY, but this is the X divided by Y. And this says is angle changes. And this we will define epsilon xy. I'm just trying to explain in easier way, okay? Rather than going through all different equations, complicated equations. And I hope that this will be much easier for you to understand. And another thing is that, okay, we have this body, and let's say we have this much angle changes. Okay? And see, in two-dimensional case, the angle will change in this way, this guy. And see, this one and this one need angle change together, right? And now the other one we can consider, okay, so this one changes like that, and this deformation is called, is it X directional display or Y directions? y direction, delta y, and divide by this Lx, and which will give us these angle changes, right? So we can say this is the epsilon yx. But here, see, here, this deformed shape, if we just rotate, this will be same as that one, right? This one and that will be same. So not just same. I'm sorry. I will correct my statement. It's not the same, but will be very much similar. So we will define. This is not the correct definitions. It's just I would say just conceptual explanations. And actually, epsilon xy. Now we define a combination of this one and this. Combine them. We combine them, okay, and divide by half, and that will be called epsilon xy. So anyhow, that's the descriptions. In mathematical way, see, ux and uy defined at a point O, and each point we will have in y plus dy. Where is the y plus dy? Okay, let's see where. Oh, E. So this point is the x plus xy plus dy, so this one. So point is that here we have the ux and uy, and the displacement at this point is defined incremental terms, which is in y directions because of a y directional increment. So we have this partial derivative dy and dy, and you have incremental terms. And same for point C. We have a dx, so whatever we define ux and uy, there will be an increment due to an x directional increment. So x and x, ux dx, and delta y, delta x, and same for uy. So this is the displacement at a point E and point C. Now x-directional normal strain, xx is that x-directional length, the elongation divided by length, which will give us x, ux divided by x. Okay, what is u? What is ux and uy? Ux and uy is the displacement, and displacement vector at a point O, and so conceptually this will be very much like delta x divided by Lx. Displacement is defined as a movement at a point O, whatever point, in certain directions. Certain direction denoted by whether x or y. So ux means that at a point O, it needs to be moved in certain directions. So here we have a displacement, and this will be a ux and uy, and this point O will move to a O prime, and that is the displacement. And this displacement will be defined every point. Every point. So if we go through this expression, same for y directions. The only difference is that Lx, what is Lx here? We have a dx. And x-directional displacement here, to get this one, the difference is that this one and this one and originally there was the ux. And deform movement is this one, so if this one minus this one will only, we have this one. So this is the x-directional displacement. And divide by dx give us these partial terms. This is the x-directional strain. And same for y-directional strain. And now y-directional, okay, shear, remember that angle changes. We have two terms, and if we define these two terms, we have this way, this define. So shear strain, we will define angle changes this angle changes. We will have two different angles. This one and that one is called theta 1 and theta 2. And this strain will be defined as the summation of those two angles and average them. Half. And that's the shear strain. Okay, so this is the two-dimensional strain, and we have epsilon xx, epsilon yy, and epsilon xy, and epsilon yx. Epsilon xy and epsilon yx, they are same by definition. We define that way. So epsilon xy and epsilon yx, those are shear strain, angle changes, and they are same. And as you can see here, 1, 2, 3, 4, we have 4 terms, means that in two-dimensional space we have a 2 by 2. And three-dimensional, we can just extend in this concept, and rather than rectangular, what do we need to consider? We need to consider a volume. Volume, it extends this way, this way, and it has an angle change this way, and that way. So we have a 3 by 3 component like that. Now, well, we define stresses, we define strains, and next step, of course, define the relation between stress and strains, material properties in general sense, and normal stress-strain relation, okay, which means that this body is very much similar to a bar in a one-dimensional case. We have a bar like that and subject to a normal stress like that, sigma xx, then this will deform in x directions, and epsilon xx is the x-directional strain, and the relation between sigma xx and epsilon xx is the Young's modulus, right? Young's modulus. And this Young's modulus will also equally apply to y directions and z directions. So we have epsilon xx and sigma xx, and epsilon yy and sigma yy, and epsilon zz and sigma zz. That's what normal stress relations. But there are more. As you can see here, when this body is subject to extractional, this extractional stress is causing epsilon xx for sure. But what else does this sigma xx cause? Well, it causes contractions, right? It causes epsilon yy. It also causes epsilon zz. Sigma xx will cause epsilon xx, epsilon yy, and epsilon zz. But epsilon yy and zz, we have the Poisson's ratio, right? There is a ratio called Poisson's ratio, and Poisson's ratio is the ratio between x directional strain and y directional strain. And x directional strain, we already have epsilon xx, so we just multiply Poisson's ratio times this epsilon xx. That is the epsilon yy or epsilon xx. So again, sigma xx cause these three components, and same for sigma yy. Sigma yy, we will have the normal strains epsilon yy, and x and z direction we will have a contraction by Poisson's ratio. Okay. So let me rather than this expression will be better for you to understand. Epsilon xx, epsilon yy, and epsilon zz. And see, if you have epsilon xx, epsilon yy, and epsilon zz, this one, epsilon xx, will be, there is 1 over e. See these relations, 1 over e. And this epsilon yy by sigma xx will be Poisson's ratio. Actually this one. And there will be a epsilon like that. Okay, in other words, if you apply sigma xx, then we will have a three component of strains, which is the epsilon xx times this one, and epsilon yy. Now you need to have a Poisson's ratio. Remember, you have a Poisson's ratio divided by Young's modulus times the sigma xx, right? So times this one, and same for epsilon zz. Now, how about if you apply sigma xx? What are you gonna do? What are you gonna have? You're gonna have 1 over e epsilon yy, and this one will be, you have minus mu over e minus mu over e. Right? Pay attention to this diagonal term. Right? And now, how about the sigma xx? I mean zz. You're gonna have 1 over e minus mu e minus mu over e. Same thing. Well, I'm just using this notation instead of this. How many equations? We have many equations, but we just use this simple expression. You know, remember f equal kx? Now this expression is nothing but x divided by 1 over k times f. See, instead of f equal kx, we divide by k here, then x equal f divided by k, right? So this is a one-dimensional material properties. And compare this one, we have a displacement and stresses. There are 1 divided by stiffness every terms, and same for the spring constant. And remember, these relations are only for normal stress component. This is the xx, yy, zz. xx, yy, zz. Those three terms are from this guy. Only these three terms. Okay? Only these three terms of strains and 3 terms of strain. This again, this equation are only for those 3 diagonal terms. Now, how about the other shear strain? Shear strain. And here we have sigma xy. Well, it looks very complicated, but sigma xy. Each surface we have a 2 component of shear stress, and this one 2, 2, 2, and this sigma xy we have a sigma xy here, sigma xy and sigma yx. And either cause a strain, deformation, this one. So deformation and stress, there is the, very much similar to us. Epsilon xx equals sigma xx divided by E. Similar to this expression for shear is a sigma xy, not xx. xy, we have a material properties called G. Very similar to E, Young's modulus E, there is a G. Okay, now why there is a 2 there? 2. Well, that's just the definition. And shear strength, when we define, we use the 1/2 divided by 1/2. Well, that was the kind of reason why we have the 2 here. But just say this is the definition of a G. Okay, definition of a G. And G is called what? G is called shear modulus. Shear modulus. G is called shear modulus. And G, we have a relation E to 1 plus mu. Very important relation, and we can always drive these relations. And this means that once we have the Young's modulus and Poisson's ratio, the shear modulus G can be always calculated. And you need to understand these relations. Okay, E divided by 2, 1 plus mu. Now, let's put them all together. And see the first one. Remember that epsilon xx strain will be caused by sigma xx divided by E, and epsilon yy will cause again epsilon xx by Poisson's ratio, and same for sigma zz, there will be a Poisson's ratio. And this relation will be similar to y direction and the z directions. And there are 3 equations for shear. So how many equations do we have totally? How many equations? We have 6 equations. 6 equations. And we put into a matrix, and that is this one. Same as this one, but just use the vector form and matrix form, right? This is 3, 3, 3, 3, this one, and this is sigma x, xx, yy, zz, and we put it here, and then we have diagonal and over diagonal terms, and others are 0. Others are 0. That means you have no shear stress contributions. And epsilon xx, epsilon xy has only has a relation with sigma xy. So as you can see here, this sigma yx or xy have a sigma epsilon yx. And same for others. So you have to understand and you have to memorize this equation. Okay, you can always epsilon xx, yy, zz, xy, yz, zx, and right hand side same sigma xx, yy, zz, and yz, zx, and xy, and there is a diagonal terms and over diagonal term. It's not that difficult to memorize them, but this one understanding it really helps you calculate strains when you have the stresses. Okay, so this is the final equation. Just one more, last one. We are looking at material properties, stress-strain relations, and there is another one called CTE. Thermal CTE means the coefficient of thermal expansion. Let me put it this way. We have a spring F equal to Kx, and this is the spring. Okay, this is a spring. Now, we do not apply any load, but instead we apply heat, increase the temperature. Increase temperature. What will happen to this spring? Spring will expand, right? Spring will expand, right? Remember, there's no load, but spring will extend. Extend. How much? Extend spring by delta T. How much? Okay, let's define alpha. Right, this is the equation. X equal alpha delta T. Now this is actually more important than this complicated equation. That simple understanding is the one you need to fully understand. Now, in addition to this temperature, you apply load at the same time as the delta T. So we have F here, F, and we have delta T here. Same, at the same time. Then deformations. See, we have force, deformation due to force, which will be F divided by K, and plus alpha delta T. Yes. That's the what deformation we will have in spring, which is subject to a delta T and force at the same time. We increase the temperature and we apply load at the same time. So deformation is always F, remember this equation, F divided by K plus alpha delta T. That's the equations. Okay?
Yes.
Okay. Now exactly same to this three-dimensional body. In three-dimensional body, similar to x equal alpha delta t, we have epsilon xx, yy, epsilon zz in all direction. So if a body, we increase the temperature, this will expand this way, and that way, every directions. That's why we have a xx, yy, and I'm sorry, xxx. But temperature wouldn't change angle. See, temperature always, if this body and always deform like that. Temperature will cause deformation like that. In other words, temperature will not have this kind of a deformations. There is no such a deformation, which means that there will be no shear. Temperature always cause normal strains only. So anyhow, this strain or this x, this is the F divided by, see, this is a E here, this one, and alpha delta T, same as this one, alpha delta T. So only difference between this spring and three-dimensional body is that we extend the idea or concept from one-dimensional to a three-dimensional space. In three-dimensional space, instead of force, we need to have a 6 or 9 component of a stress, right? We have a plane and 3, this plane 3, this plane 3. And instead of an expression of simple deformation, we need to have a, we need to have a 6 component of strain. Why? We have a one dimension, this length, that length, angle change, and so on. Right? So this is the final equation, and it's not that difficult to understand and memorize them. And the material property for each one, let's say steel, okay, material steel, aluminum or steel. The one material property I want to memorize is that steel. What is the Young's modulus for steel? 200 gigapascal. That's the number you need to memorize. 200 gigapascal. See here, 200. This is the about 200 gigapascal for material of steel. Steel material has the 200 gigapascal Young's modulus. And Poisson's ratio is what? 0.3. And shear modulus G, you don't have to memorize them. You have a relations E divided by E 1 plus, 2 times divided by 2, 1 plus mu. That you need to always calculate. And alpha, well, you need to memorize them. This is a 10 to the minus 6. Okay, 10 times 10 to the minus 6. That you need to memorize them. Okay? So in midterm or final term exam, if I say steel, then you have to use these material properties. Okay? Do not ask what is the E and what is the alpha. You have to have this value. Especially this one, CTE, coefficient of thermal expansion, is that 10 times 10 to the minus 6. per C. Why per C? That's the definition of a CTP. Any question? Okay, so see you next week. Thank you.